So here we are, finally, part 4. This is the last part of digestion. So I'll be talking about what happens from after the stomach and in the small intestine, okay? This is only that digestion, so we're only finishing now the breakdown of the food. After digestion, it will be absorption, but that's for another video. So first we'll label what's going on and what's important in the last part of digestion. And then I'll use this diagram here, which is I think it's a pretty good diagram that I made that will help explain exactly and visualize exactly what happens. Because I find it's easier to learn when you can actually see what's going on. So first let's label. So the liver. Many people don't know where this is because they get confused with the liver and the stomach. But the liver is this organ right here. The way you know it's not the stomach is because the stomach is directly attached to the esophagus, this pipe, okay? Whereas the liver is not. So that's the easy way. Another way is if the diagram isn't good that you're given in the test, the stomach is normally 99.9% of the time it's on the left side of the body. So this guy's looking towards us, so it's on his left side. Whereas the liver is always on the right side. There is this 0.001% chance that your body is a little bit abnormal and everything is switched around, but in most people it's this way. Next we got let's go first with the pancreas. So the pancreas is right below the stomach. The pancreas is super important later. We'll talk about this. That's why I made it yellow. Okay, small intestine. Small intestine is the final part where food is digested. The small intestine is directly connected to the stomach. So we got the stomach. It will travel down and become the small intestine right about here. And then it will continue and be the small intestine for like 7 meters. Really long. And don't be confused with the small and large intestine. The small intestine is the longer one, so it sounds contradicting, but it's true. So the small one is the longer one, but I think of it as the small intestine is quite thin, so I think it's smaller, whereas the large intestine is quite thick, so it's the large intestine, but the smaller one is much longer, okay? Next, gallbladder. Gallbladder is right attached to the liver, so right there, this green blob right there. Also important. Okay, the bile duct is an important thing that you need to know how to label, but it's not in this diagram. So later in this video, I'll have a better diagram, but that will show this pretty good. So I'll move it there. We'll do it later. Okay, peristalsis. So let's catch up to where we're at. So in the final video, we were talking about how the proteins were digested in the stomach. Okay, and it formed all your food now together that's been digested from the mouth to the stomach forms this brown-like liquid called chyme. Now, this chyme is ready to move into the small intestine to be further digested and finished digesting. Now, remember peristalsis. I mentioned that it is related to the esophagus, how the esophagus moves food down towards the stomach. Now, this is true, but peristalsis is not only limited to the esophagus. This is the same mechanism used by the small intestine to move food all through the small intestine. So peristalsis also applies to the small intestine to move food, not just the esophagus. So bear that in mind. Okay, now to clarify, so far up till after the stomach, we have this. So we started digesting carbohydrates, right? So I'll give it a tick. But at the same time, we didn't finish it. We made, so far, maltose from so for example, when you're in the stomach, in the mouth, your carbohydrates are broken down into maltose. But maltose is not the final product we want from our carbohydrates. We want glucose. So I'm putting a tick and a cross here because we started digesting our carbohydrates into maltose, but it's not finished yet because we want glucose. At the same time, in the stomach, we started digestion of the proteins. But again, we didn't finish. We converted our proteins in the stomach into polypeptides. So we got polypeptides right now. But polypeptides is not the final product we want from digestion. We want amino acids from our proteins, not polypeptides. We want the smallest unit possible, amino acids. So far, our carbs and our proteins, we've started but not finished digesting. And our last macromolecule, the fats, we have not touched at all yet. We have not even started breaking down our fats by this point. So this is where we're at. So now that we're on the same page, let's move forward. Okay, let's bring this down. So just so you visualize where we are, I got this diagram here. So when you look at the stomach, this is the stomach, our chyme is now moving into this little pipe here. This little pipe is the beginning of the small intestine. Okay? Wait a second. So I'm going to label the bile duct for you guys because it will make more sense. Okay, so the bile duct, we couldn't see on this diagram here because it's really, there's no duct. But this diagram is more clear. This is the bile duct. The bile duct is a little pipe. It's a little pipe connecting the gallbladder into your small intestine. Okay? So this green duct right here is the bile duct. Now what happens is, when your food is in your stomach, your body knows that the food is really close to the small intestine. So when your food is in here, your body sends signals to both your bile duct, your liver, and your pancreas, and stimulates them to start releasing things into the small intestine, because it's important to be ready. So your body needs to be ready to receive the food from the small intestine, from the stomach. So the next phase will be the food going from the stomach into your small intestine. But your small intestine needs to be ready. It needs to have all the liquids and stuff inside ready to break down the rest of your food. Because remember, we need to finish breaking carbohydrates, we need to finish breaking down proteins, and we need to finish fats. Because I told you, this is the last stage. This is the last stage of digestion. So we know all of this got to finish. By the end of this process, we need to have all ticks, no crosses. So, what exactly is released? So your food is here. Right when your food is here, your liver will start, your liver and your gallbladder will start releasing something through the bile duct into your small intestine. So this blue pipe is the small intestine, just imagine. It will start releasing this liquid called bile. So bile. Just bear the names in mind for now. Bile. So this green liquid is bile. Now the pancreas, so this yellow organ right here, is going to release into this pipe, this blue pipe, is going to release pancreatic juice. This is this red blob I'm showing here. So you can imagine into this pipe, both bile and pancreatic juice is being released into the small intestine. Now, okay, what does this mean? So the pancreatic juice, in my opinion, is the more significant one. It matters more because the pancreatic juice is a liquid that includes four important things that you need to know. So the pancreatic juice includes lipase, endopeptidase, amylase, and bicarbonate. Three of these things that the pancreatic juice is three enzymes. You can see their enzymes because they end in ase. And enzymes, we know, break things down. So that's good. We want to break things down more. So these three seem like they'll be useful. What the hell is bicarbonate then? Okay, this one is not an enzyme. We will talk about this one near the end of this video, but it is super, super important. So make sure you stay until this part. Now, the names are pretty nice. They make sense to what they do. So first, what does lipase do? So think about our problem. We want to finish this. What do you think lipase will do? What does lipase sound like? Lipase to me sounds like lipids, right? Lipids. And we know lipids is fats. It's another name for fats. So I would say that lipase will break down the lipids, or the scientific name, if you need to know, is triglycerides. So it will break down lipids or triglycerides into glycerol and fatty acids. That means when this happens, we are officially finished with lipids. Yes, so one macromolecule is finished. We still got to finish these two. But bear in mind that lipase does not work on its own. Bile, remember, bile made by the gallbladder, it's made by the liver and stored by the gallbladder, by the way. So the liver is going to make bile, the gallbladder is going to store it, and the gallbladder will release it through the bile duct into the small intestine. Now, bile is basically lipase's friend. They do teamwork to finish this process. So lipase doesn't work alone. They both of these two work together. This is an enzyme, this is not, but they both do the same thing, okay? That's basically the purpose of bile, to break down fats along with lipase. Now, next one, endopeptidase. What is endopeptidase going to do? Remember that so far, for the protein aspect, we broke down proteins into polypeptides. So we're not finished yet, we want amino acids. Now, endopeptidase sounds a lot like polypeptides. Peptides, right? Endopeptidase. Now, exactly, so that enzyme, endopeptidase, will break down polypeptides into amino acids. Okay? Now, proteins are finished. See? Now there's no more cross on the proteins. Proteins are finished. Now the last one we seem to have left is carbs. So remember, so far we broke down the carbs into maltose, but maltose is not the last thing we want. We want glucose, okay? Because maltose and polypeptides, they're both too big to be used by our body, so we need to break them down into glucose and amino acids. Otherwise our body can't use them. They're just simply too big. So that's what amylase is going to do. You might think, oh, I've heard of amylase before. You're right. Amylase is also an enzyme in your mouth. Do you remember salivary amylase? That was the enzyme released by your salivary glands to break down starch or any kind of carbs into maltose. So amylase is what we use to make maltose, but we used salivary amylase. In this case, we're using pancreatic amylase. So they're actually different. They have a similar name, pancreatic amylase and salivary amylase, but they do slightly different things. Salivary amylase, discussed in video 1, breaks down carbs into maltose. Pancreatic amylase will break down maltose into sugar. Or glucose. Glucose is the science name. Maltose into glucose. So this is pretty simple, right? So now we actually have all of them finished. They're all broken down. But remember, I did say that bicarbonate is important. So it is really important. Without bicarbonate, none of this can happen. So if you have all three of these but no bicarbonate, well, then none of this can happen. So everything that we just talked about would be useless without bicarbonate. So what does bicarbonate do? How can it be so important? So bicarbonate, remember, in your body, so yeah, basically we'll talk about this right after. It's a mechanism that might be useful to know. So we'll talk about that. But first, remember, do you recall that the pH is important for enzymes to work? Do you remember? So the three enzymes we got here is lipase, endopeptidase, and amylase. So lipase, endopeptidase, and amylase. And enzymes only work under certain conditions. Okay, they're annoying. They only work under certain conditions. They don't always work. The conditions that these three enzymes specifically need is pH 7 to 8 and 37 degrees Celsius. But do you remember the enzymes in the stomach actually needed pH 2, a much lower pH? So that's weird. So you can think about it. The food coming from the stomach, the liquid coming from the stomach into the small intestine will be really acidic because it's pH 2, right? So that would mean the liquid coming into here from the stomach is going to be really, really acidic. And that's really bad because that means the pH will be really acidic. And that means none of these enzymes can work because they need pH 7 to 8. So that's really bad. So we need to fix that. And that's exactly what bicarbonate will do. So in your stomach, the pH is like 1 or 2 or 3, really, really low, okay? And you can imagine this liquid from the stomach will come into the small intestine and also make it acidic. So what we need is bicarbonate. Your body predicts everything, so it's pretty smart. So bicarbonate that is released in the pancreatic juice just mentioned will change the pH. So it will it will react with the acidic pH of the stuff coming from the stomach. So the stuff will directly come from the stomach into the small intestine, and as it's coming in to the small intestine, bicarbonate will react with all that stuff that is acidic and make it neutral. It will make it neutral around 7, maybe a bit higher, because maybe there's too much bicarbonate, because bicarbonate is a base, and we know that when an acid and a base reacts, it becomes neutral, so it's neutralized. A base is basically the exact opposite thing of an acid. So when they react, they kind of neutralize. So that's really smart. So as this stuff is coming from your stomach into the small intestine, bicarbonate that was released in the pancreatic juice will react with all that acid and make the solution neutral, fairly neutral, 7 to 8, around there. And this is great because now that the pH in the small intestine is where it's supposed to be, now all these enzymes can actually work and break down your food. And so everything is broken down into the smallest units possible. Glucose, so we got glucose, amino acids, glycerol, and fatty acids. All these 3 things are really useful now because they're small enough to be used by your body, okay? From all these 3 things, you can build muscle, you can make fat, you can make proteins, and everything in your body that makes you function well. So that's the use of bicarbonate. You can see how it's so important. Without this, the stuff coming from the stomach would not be neutralized, and that would mean that the small intestine will also be acidic, and that means none of the enzymes will work. Okay, so no bicarbonate, this situation, and this situation is just not good. Okay, so one last thing that will be useful is how exactly does lipase break down lipids into glycerol, and how exactly does endopeptidase break down polypeptides into amino acid, and same with this scenario. So if I show you one scenario, it's the same for the rest. So let's just real quick look at this. So I used the same kind of diagram in all the other parts that I used, so maybe you're familiar with this. So what is the source of lipase? So this diagram here is just for lipase. So what is the source of lipase? Lipase comes from the pancreas. We know that. It's released from here in the form of the pancreatic juice. The pancreatic juice contains lipase. So lipase, the source is pancreas. And let's pretend it looks like this. It doesn't really look like this, but just for the sake of now, you don't need to know how it actually looks like, so it's fine. So this enzyme, we know, only breaks down triglycerides. Remember, enzymes are special because they only do one thing in life. They only have one purpose. They don't do anything else except that one thing they're destined for. And lipase is destined to break down which of these do you think? Let's pretend the square is carbohydrates. Let's pretend this one is proteins. And let's pretend this one is fats. Which one do you think it can break down the easiest? Yeah, I would say the fats. It looks like it will go in pretty nicely. It's a fit, but it won't break down any of the other ones because that's no way going to work. So once it binds to that triglyceride, it will break it apart into the products, just like this. So the products include fatty acids and glycerol. And remember, the enzyme itself is never affected in the process of doing so. So right after it breaks down the substrate, in this case triglyceride, into the products, the enzyme itself is not affected, which means it can now go off and do it again with another molecule of fat. And then after that happened, it can go do it again and again. And that's great because every time, that means they can do it really fast and do it for a really long time. If they weren't able to do this and they would be changed in the process of reacting, that would mean you'd need a lot of enzymes to be able to break down your food, and that's bad. So this way we don't need that many because they can be recycled or reused. And you can imagine this process is the same for the rest. So for example, endopeptidase, the source would be pancreas. The enzyme's name is endopeptidase, and the substrate is not triglycerides, it is polypeptides. So endopeptidase, the enzyme, would break the substrate for endopeptidase would be polypeptides. Polypeptides would bind to endopeptidase and be broken down into the products, which would be amino acids instead, and the enzyme itself would be unaffected. Amylase is also, pancreatic amylase is from the pancreas. The enzyme name is amylase, pancreatic amylase. The substrate would be maltose. The substrate is the thing destined to be broken down, okay? So the substrate of amylase is maltose. Once maltose binds to amylase, amylase will break it down into the products, which is glucose, and the enzyme amylase will be remained unaffected. So if you understand this concept, that's how all enzymes basically work. So I hope this was useful, and now we have broken down everything into the smallest pieces they can be, so digestion is finished. I will make some questions on all the stuff involved in digestion, IB questions, so that'll be useful for your tests. And then after that, we'll go into absorption, how these small molecules that we formed, glycerol, fatty acids, amino acids, and glucose, how these molecules are now going to be transported into our bloodstream and actually be used for once to do something useful in our body. Because right now, they have not been useful yet.